Now we want to spend some time talking about a pretty complicated example for Hess's law. So this is the problem. There's annotated slides in the PDF if you want to kind of follow along with those, but I'm not going to narrate it right here. We're just going to go into me working it out, where I kind of talk overall through this whole problem and give some context on it and see how it goes.
All right, so let's do an example where we're going to put all of this Hess's law ideas together. Get about as complicated as you can. You'll be preparing SOCl2 using the following reaction. SO3 gas plus Cl2 gas becomes SOCl2 plus SO2 gas. Before running the reaction, you want to know delta H. You cannot find a value for this reaction, but you were able to find delta H for some related reactions. All right, so this is a real life why we use Hess's law in the chemistry lab. You're going to do this reaction. You want to make SOCl2. And you're going to run this reaction. You're going to react SO3 and SCl2, and you're going to make this as your product. You'll have another desired product. You have another product there as well. Okay, and so you want to know delta H. And the reason why you want to know delta H, that is your enthalpy, right? That is going to correspond to let you know, is this reaction going to get hot? Is this reaction going to get cold? Is this thing exothermic, endothermic? Those are going to be some safety considerations that you need to know when you're running this reaction. Is it going to get really hot? Should you run it on ice? Is it going to get really cold? Should you maybe heat it up to keep the reaction moving? Can you put it in water, or is it going to freeze that water, right? What sort of things do you also need to be concerned with, around those ideas? That's kind of part of, doing safe chemistry, is knowing not only what you're going to make, but what the energy associated with that is. So this is a big part of being careful, not just kind of haphazardly running chemical reactions. So there's no delta H for this. You can't look it up, but you find these other reference reactions. You'll note they're both combustion reactions. It's very common to be able to find delta H for combustion reactions. These are tabulated in large numbers. And so SO2 plus O2 gives you SO3, and SCl plus O2 gives you SOCl2. And so they each have an associated delta H going across. We want to know the delta H for this reaction. And so we have two reference reactions. So the previous examples, we've kind of seen how we can add reactions together and how we can modify reactions to look like each other. And so we're going to put those ideas together in this process. So the first thing I want to do is, there's a kind of a gut reaction when you see two reactions like this, that you want to add them together. That's not what you want to do here, and what I'm going to do it to show you why it doesn't work. So let's go ahead and write them out. Our two input reactions. We can go through the process of how we learned how to add. Let's see what that looks like. SO2 gas plus O2 gas. I'm just writing out those references that I found. And our kind of gut is, hell, just add them together. We got these two. Plus O2 gas gives me 2SO-Cl2 gas. All right, I've just copied my reference. I'm going to add them together. And we know for adding together, draw an arrow. All my reactants stay reactants. All my products stay products. SO-Cl2 gas. So just move all those. I got the 2SO2 gas plus 2SCl2 gas. Plus, I'm going to combine those, 2O2 gas. Wonderful. So if I add those two reactions together, this is what I get. I don't care though, because this is what we want. Right? This is the reaction we actually want. This reaction, you can figure out its delta H. We know the delta H of this one is negative 198.2 kilojoules per mole. The delta H for this reference is 456.1 kilojoules per mole. So for this, your delta H for that total reaction is going to sum up. So just add those two together. It's going to be negative 198.2 kilojoules per mole plus negative 456.1 kilojoules per mole, which gives you a nice total of negative 654. So this is true. The enthalpy of this reaction is negative 654.3. And if that is what you wanted, you were interested in doing the reaction of SO2, SCl2, O2 to make SO3 and SOCl2, you now have the delta H. But importantly, that is not our target reaction. So we want to be careful. The kind of gut instinct that everyone has when you see these two, just add them together. And we do need to add reactions together, just not these reactions. We need to think about how can I change these in order to into a form that when I add them together will give me what I want. So how we do that is we take a look at our reference reactions, we take a look at our target, and we think again, kind of when we were rearranging, when we were changing the coefficients, changing the order, how are they similar and how are they different? What I really want to key in on is, do I have anything that is only in one of the reference reactions? So for example, SO2. So I can see SO2 is only in this one reference reaction, and it only shows up in this on the product side. And so what I can say then is, well, what I want to do is this first reaction, when I add it together, get it into a state that it adds, SO2 needs to be a product, and it needs to have a coefficient of 1. So what I'm going to do is I'm going to modify reaction 1. There's a couple things I need to do. I need to switch the order, or switch sides, and I need to change coefficients. And what I need is for them to be 1/2. So if I look, this reaction, which we'll call 1, call that 2. So for 1, it was 2 SO2 gas plus O2 gas becomes 2 SO3 gas. And we know in that case that delta H of reaction 1 is negative 198.2 kilojoules per mole. But I want to switch sides and I want to multiply the coefficients by 1/2. So this, instead of 2SO3 as a product, becomes just SO3 gas as a reactant. My products now become, instead of 2SO2, just becomes SO2 gas plus 1/2 O2 gas. And the delta H on this is going to be equal to negative 1/2 times that delta H1 that I had before. So negative 1/2 times negative 198.2 kilojoules per mole is positive 99.1 kilojoules per mole. All right, so we got reaction 1 set. Now we need to fix reaction 2. And so if we key in on reaction 2, I could say, look at, like, for example, SCl2. And SCl2 is right here. And so this is a reactant. This is a reactant. So I don't need to change sides. The only thing I need to do is adjust my coefficients. So if I modify reaction 2, I need to, the sides are fine, I just need to change coefficients. And what I need to do is I need to multiply by 1/2 because my reference is a 2, my target has a 1, but they're on the correct sides. So that's good. So what I can do is I can take that, write it out. So reaction 2 is 2 SCl2 gas plus O2 gas becomes 2SOCl2 gas. Oh, and I know delta H on that. And so what I'm going to do is I'm just going to multiply all the coefficients by 1/2. So I get SCl2 gas plus 1/2 O2 gas becomes SO Cl2 gas. And delta H on this is just going to be 1/2, no negative this time because I'm not changing, I didn't change the direction. Kilojoules per mole, which is equal to 228.1. Negative 228.1 kilojoules per mole. So I've got my modified reaction 1, got my modified reaction 2. I modified them to look like the so that the substances in those reactions were on the right side and have the correct coefficient, as in my target reaction. And so now I combine them. And so that is what it was, SO3 gas becomes SO2 gas plus 1/2 O2 gas, SCl2 gas plus 1/2 O2 gas becomes SOCl2 gas. Delta H on this one was positive 99.1 kilojoules per mole, and delta H on this one was, what we just did, negative 228.1 kilojoules per mole. And I'm going to add them together. So all of those reactants come together. SO3 gas plus SCl2 gas. Then I give myself enough space. All my reactants come together. And then all my products come together. After I combine, I want to simplify. I have O2, O2. Those need to be canceled because they're not changing. All I'm left with is then SO3 gas plus SCl2 gas becomes SO2 gas plus SOCl2 gas. Which isn't really that exciting because that was what we were told was the reaction we wanted to do. So it's good we have gotten the right reaction. Okay? It's not too nuts that we got it. We on purpose, we're trying to accomplish that. So the thing we want to take from it then is what is the delta H? And it's going to come from adding these together. Because if these were the reference reactions, adding those together gives you this. So delta H for this reaction is the sum of those two values. So that tells me that delta H is equal to positive 99.1 kilojoules per mole plus negative 228.1 kilojoules per mole, which is equal to negative 129 kilojoules per mole. Oh, sorry, 128. Yeah, 129.0. Ooh, 129. And so that's really valuable. We got information about this reaction without having to do any experiment. And it's a piece of information we would definitely want to know before running the reaction. Okay, so it's an exothermic reaction, but that's not very exothermic. Negative 129 isn't too bad. If we had taken the result of just adding them together, we got negative 650. That's a very exothermic reaction. We'd probably be a lot more concerned about trying to keep this thing cold and make sure it doesn't get super hot. We still need to be mindful. This thing will be getting warm, but it's probably not going to get scaldingly hot. We don't need to take too crazy of adjustments. But we can go through this process. We did not do any experiments here. We just looked up reference data and we learned something about this experiment that will be valuable. We learned something about a chemical reaction without having to do it. And that's really, at the end, the goal of doing thermodynamics.